Hello, welcome back. This is Calc 1 by Dr. Oz. So this is the second video in a series of three on antiderivatives and indefinite integration. In the first video in the series, we achieved the learning objective of writing the general solution of a differential equation and using indefinite integral notation for antiderivatives. And remember that we had the slanted S notation, f of x dx, referring to the integral of f of x. So in this video, we're going to use the basic integration rules to find antiderivatives. And hopefully after you watch this video, there's going to be another video, which is going to be the last video in a series of three, on how to find a particular solution of a differential equation. All right, as you see that you have f prime of x here, so that's in fact f of x dx, little f of x dx. And here, capital F and little f refer to the antiderivative and the original function, respectively. So if you integrate the derivative of a function, well, you should go back to where you start, which is, in fact, the capital F plus an arbitrary constant. So this is sort of like what how the relationship goes between the derivative and the antiderivative of that function. And similarly, if you do have the antiderivative of the function, let's say like this is capital F of x plus c, okay, so then if I take the derivative of both sides, I should get the same thing, right? So in other words, the derivative of the left-hand side should be exactly where you start with little f, okay? So the antiderivative of f is this integral here, and the derivative of the antiderivative is just doing and undoing, so you should go back to where you start. Okay, so for that reason, differentiation is the inverse of integration. So by keeping this in mind, that we can go back to the differentiation formula card that we had earlier in chapter 3. In fact, a copy of the PDF file is already provided in the Blackboard module. So we can go back and forth between differentiation and integration as you think that they're inverse operations. So for example, in the differentiation formula card, you had the derivative of a constant to be 0. So we talked about this, and we know this rule perfectly. So then the anti-operation for this should be like this. So the integral of 0, in fact, 0 function, should be a constant, an arbitrary constant. So 0 integrated should be giving you a constant. So as you see that from c to 0, you go with the differentiation. From 0 to the c, you go with integration. So that's why these are anti-operations of each other, okay? And similarly, in the same fashion, you have the derivative of constant times x. And we said that this should be just a constant. In fact, you can pull the constant out and then you take the derivative of x. That's k. So that means that if I integrate a constant, I should go back to kx, and I should also add the integration constant here. Okay? So k, a constant integrated, should give you k times x. And if you want to generalize this, so the derivative of k times any function is k times the derivative of that function. In other words, you can always pull out constants in differentiation. I can do the same thing for integration. So if I try to integrate k times f of x dx, it's equivalent to saying that this integral is equal to k times the integral of f. Okay, in other words, k can be always pulled out of integration. And we had another operation that was allowing us using the divide and conquer technique. So if you have two functions added or subtracted, when you take the derivative of that, it's equivalent to take the individual derivatives and carry forward the plus or minus sign. And you can do the same thing in integration or anti-differentiation. So integral of the sum or difference of two functions is the sum or difference of the integrals of two functions, essentially. Okay, and one final rule that we're going to use extensively in this chapter is the power rule for differentiation. All right, power rule for differentiation. Essentially, if you take the derivative of x to the n, you put the exponent down and you just subtract 1 from the power, so that takes you back to n times x to the n minus 1. Okay, There's a similar rule for integration, but we're sort of like doing exact opposite of what we do in differentiation. So if you integrate, in other words, x to the n, this time we're gonna add 1 to the exponent and divide the whole thing by n plus 1. Okay, so here, remember, we were putting the n down. That means you're multiplying by n and subtracting 1 from the power. So now we're adding first and then dividing. Okay, subtracting becomes adding, multiplying becomes dividing. And we also add arbitrary constant or integration constant at the end. And this formula is true whenever n is not equal to -1, because we have a special formula for the case of integrating x to the -1 dx, which is in fact 1 over x dx. So for 1 over x dx, you can't really use this formula because the bottom becomes 0 when n equals -1, right? You can't use this formula anymore. And you will see like 2 slides after, I am going to talk about that. Okay, so for now, if you want, you can pause the video and then sort of like get familiar with these formulas. But I'm going to continue with developing formulas for basic trig functions. And we had a similar version for differentiation earlier. For example, sine has the derivative cosine. So we're going to do the ni operation again. So if I integrate cosine here, so integral of cosine x dx should be sine x plus the arbitrary constant. And I can do the same thing for, let's say, cosine x has the derivative of negative sine x here. So if I integrate sine x, then be careful about this minus sign here. So if I just integrate the sine portion of that, that means that the integral would be minus cosine x plus c. Okay? Or if you look at the derivative of secant x, we had secant x tangent x. Then if I try to integrate secant x tangent x, I should get back to secant x plus c. All right, so again, even for this slide, you can pause the video and try to get familiar with these formulas. And then finally, we're going to have 3 more formulas, 2 of which cover integration of exponential functions, and the last one is for the logarithmic rule for integration. So essentially, we had the derivative of e to the x to be just e to the x. We had this rule before. So that means if I integrate e to the x, in other words, if I look at integral e to the x dx, the result should be e to the x plus the integration constant. Okay? And we had the derivative of a to the x. So a is a number different from e, let's say. Okay, so then the derivative of that would be ln a times a to the x. So I essentially multiply a to the x by ln a. So this time, when I do the integration, I'm going to divide. So multiplication becomes division. So 1 over ln a times the same exponential function plus an arbitrary constant. Okay? And going back to the differentiation of the natural log, we had 1 over x, and x is always positive here. So if we try to integrate 1 over x, and that's essentially what we skipped in the power rule for integration, right? That's the integral of x to the -1, because 1 over x is just the reciprocal of x. So new rule, so we don't really use power rule in this case, because if you use power rule, the bottom in the integration becomes 0, right? This part becomes 0. We don't want that because we are not allowed to divide by 0. So this is defined as the natural log of absolute value of x plus c. And here the absolute value is important because ln function is defined for positive inputs. So by putting the absolute value, we make the input positive automatically. Okay, so don't forget to put absolute value sign whenever you're trying to do integration of the form 1 over x dx. Okay. So let's have like a few examples to solidify these rules and understand these rules better in applications. So let's say like I'm trying to integrate 3x dx. Well, first thing is first, I can always pull out the constant by using the constant multiple rule. So we can easily make 3 out and look at the integration of x dx. But x dx is a kind of integral that we can use the power rule for. So, but then to be able to use the power rule, we need to know what the power is, right? And in this case, x comes with the power 1, so it's x to the 1 essentially, right? So then by using the power rule for integration, we are going to add 1 to the exponent and divide by the new exponent. This is the rule that we're going to use. Okay, so essentially I'm gonna add 1 to the exponent and divide by the new exponent. Okay, so let's see if that's correct. All right, so if you do that, you're going to have x squared over 2 as the result of the integration. So here we go. I had 3 as a multiple here, pulled out. 3 times x squared over 2 plus c. And eventually, once we're done, we simplify our findings. So you have 3x squared over 2 plus c. All right? So this sort of like process is pretty common that we had even in the differentiation process. You write down the original integral. And then, in fact, this is already provided to you. So you rewrite that. In this case, we rewrote it because we used the constant multiple rule and we put 1 to the exponent. So this is the rewrite part of that, right? And then we integrate by using the rules of integration that we developed in these like 3 tables here. Okay, and then we simplify. Simplifying is the most important part because we may need the output to be used for another calculation, so we want to simplify it as much as we can. All right. So as a quick application of this, I want to go through. In fact, one example here, and you can do the others by yourself. So I'm going to choose B in this exercise. Okay, so essentially the exercise is asking you to integrate the given function. Okay, so you can do the others by yourselves. Okay, so I'm going to put stars here. So once you're done with this video, please go over those and make sure you got the right answer. Okay, so let's try to handle this case. Let me use another color here. So let's try to handle this. So well, you have the integral of a huge chunk here. So one property that I can use here is the divide and conquer technique. So why don't we rewrite this as the sum or difference of 3 different integrals. So here we go. I'm going to split this as like 4x dx, and I always carry forward the integral and dx along with the function. Okay, once I split, so I put the minus sign here. I put the integral sign, 7 to the x dx, and then finally I put the plus sign and integrate cosine x. Okay, as you see that the integral signs and dx's are sort of like carried forward. And next I'm going to use the constant multiple rule to pull out 4 here. Okay, so I have 7 to the x dx and I have cosine x dx. So the whole rationale here in the divide and conquer technique is that once you split everything, so individual pieces should be integrated by using the tables that we had in the previous slides. For example, we have x dx. I know that the power rule for integration is going to cover that. And I have, let's see, 7 to the x dx. I know that I have a formula for that, which is right here. Right? It's a equals 7 to the x dx is 1 over ln 7 to the x. Okay, I'm going to copy that down here in a sec. And as well, cosine x dx, I have a formula for that right here. Right? Cosine x dx is sine x plus c. And for each of those integrations, you can put one arbitrary constant, but what we do in general and in practice is that we do find one antiderivative for each candidate here, and then we add the integration constant at the end. So what I mean by that is, let's just use the power rule first, and I'll tell you about the integration constant at the end. So, well, we have 4 here, and then power rule of integration says that add 1 to the exponent, which is already 1 here, right? And then divide by the new exponent, which is what we did in the previous slide as an example. And then for 7 to the x, we had the formula, remember, this is 7 to the x over ln 7. And then cosine x has the integral sine x. So remember that instead of putting like one arbitrary constant for each, I'm going to put one generic arbitrary constant here that would take care of putting the arbitrary constant task after the integration. And the next is to simplify the output as much as you can. So here, for example, you have 2, you have 4 and 2 cancels out. So you have 2x squared. You have 7 to the x ln 7, you can leave it as is. And then you have sine x, again, you can leave it as is, plus an integration constant. Okay? And that's the final answer. If you want to have reality check here, go ahead and then take the derivative of this piece. You should go back to where you start. So you should go back to this integrand here. So in other words, for example, if I take the derivative of this by using the power rule for differentiation, so 2 times 2 is 4, it should be 4x. Here we go, I get 4x here. If I take the derivative of 7 to the x divided by ln 7, that's in fact, well, the derivative of 7 to the x is ln 7 times 7 to the x, but ln 7's cancel out, so you go back to 7 to the x. And we know that sine has a derivative cosine. And then c has the derivative 0, so you go back to this entire integrand after the differentiation process. So if you're unsure that your result is correct, then I would totally recommend you to take the derivative of the final output to see if you get the same integrand you start with. All right, and please do the other exercises by yourselves. Okay. So this is the end of the video. Thanks for watching, and don't forget to watch the next video, which is the third in a series of 3. Bye.